September 14, 1942. Boeing Plant 2, Seattle, Washington. The production line stretched across 17 acres of concrete and steel, a mechanized cathedral where America transformed aluminum and ambition into air power. Every 8 hours, another B-17 flying fortress emerged complete. Engines mounted, guns installed, ready to cross the Atlantic and challenge the Luftwaffe for control of European skies. The rhythm was hypnotic. Rivet guns hammering, hydraulic presses stamping, assembly teams moving with choreographed precision that turned individual components into instruments of war. On Station 47, where the tail assembly met the fuselage, Walter Kowalski had been installing structural bolts for 9 months. 38 years old, Polish immigrant, former coal miner who had traded Pennsylvania darkness for Seattle rain and defense wages that fed his family. His hands knew the weight of tools, the resistance of metal, the exact torque required for each fastener. He was one of 40,000 workers at Boeing, anonymous and essential, converting engineering drawings into the bombers that military planners promised would win the war. At 2:17 p.m., Walter installed a bolt incorrectly. The misalignment was slight, 3 degrees off specification, invisible to casual inspection. He noticed immediately, reached to correct it, then stopped. The structure felt different, stronger. He tested the joint, felt something unexpected in its resistance to stress. Walter Kowalski made a decision that would save thousands of lives. The Boeing B-17 Flying Fortress represented American industrial ambition in aluminum form. 4 Wright Cyclone engines generating 4,800 horsepower, 13 .50 caliber machine guns, capacity for 8,000 pounds of bombs, and a crew of 10 men whose survival depended on the aircraft's ability to absorb catastrophic damage and continue flying. The Army Air Forces had ordered them in quantities that staggered imagination. 12,000 aircraft, each requiring 420,000 individual parts assembled with precision that tolerated minimal error. The engineering specifications came from Boeing's design team in exact detail. Every rivet placement, every structural joint, every load-bearing connection calculated to balance weight against strength, cost against durability. The tail section, where Walter worked, was particularly critical. Vertical stabilizer and horizontal stabilizers, rudder and elevators, all mounted to the rear fuselage through a complex assembly of spars, ribs, and attachment points that had to withstand aerodynamic forces capable of tearing lesser aircraft apart. Station 47's standard procedure called for installation of 6 titanium steel bolts in a specific pattern, each torqued to 175 foot-pounds, creating a joint that distributed stress evenly across mounting plates. The engineering was sound. Boeing's designers had tested it extensively in wind tunnels and structural laboratories. The B-17 could take punishment, but could take punishment and nearly indestructible existed in different categories of survival. Walter understood structural mechanics not from engineering school but from 10 years underground in Pennsylvania coal mines, where improperly shored tunnels killed men with reliable efficiency. He had learned to read stress in beams, to feel weakness in supports, to recognize the subtle indicators that separated adequate from catastrophic. When he installed that bolt 3 degrees off specification and felt the joint's altered response, his hands registered what his mind couldn't yet articulate. The misalignment had created a load distribution pattern that was somehow superior to the original design. He should have corrected it immediately. Quality control would catch such deviations. Production schedules allowed no time for unauthorized experimentation. The Army Air Forces was losing bombers over Europe faster than factories could replace them. 30 aircraft per mission some days, 300 young men not returning. Every hour of delay represented American crews flying in older, more vulnerable aircraft. But Walter's hands insisted the joint was better wrong than right, and Walter Kowalski trusted his hands more than he trusted blueprints. Walter didn't report the deviation. Instead, he continued working, installing the remaining bolts according to specification, while his mind calculated angles and stress vectors with the intuitive geometry that skilled tradesmen develop. At shift change, 4:00 p.m., he approached his supervisor, Frank Morrison, a Boeing engineer who had risen from the factory floor and understood that sometimes the best innovations came from the men actually building the aircraft. "Mr. Morrison, I need to show you something." They returned to Station 47 after the evening shift departed, the production floor emptying into relative quiet. Walter demonstrated the difference. One joint assembled to specification, another with a 3-degree deviation. Morrison was skeptical until Walter applied torque to both assemblies, measuring deflection with the precision instruments kept for quality verification. The misaligned joint showed 14% less deflection under equivalent load. The stress distributed differently, engaging secondary support structures that the original design left partially idle. Morrison stared at the measurement gauges, then at Walter, then back at the joints. "This shouldn't work better," Morrison said slowly. "The engineering calculations say this should be weaker." "Engineering calculations don't spend 10 hours a day installing these joints," Walter replied. "I'm telling you, something about that angle changes how the load transfers. It's stronger." Morrison understood the implications immediately. If Walter was correct, every B-17 already delivered had tail assemblies that were good but not optimal. If Walter was wrong, they would be deliberately introducing structural flaws into bombers that would carry American crews into combat. The decision carried weight that extended beyond manufacturing. It was a question of whether to trust mathematics or hands, theory or practice. "I need to take this to engineering," Morrison said. "Don't install any more until we test this properly." "The line keeps moving," Walter pointed out. "Every 8 hours another bird rolls out. You pull me off station, that's one less aircraft reaching Europe." Morrison made his calculation. "Install them your way. Document which aircraft. If testing proves you're right, we'll retrofit the fleet. If you're wrong," he left the consequence unspoken. "If wrong, Walter Kowalski's deviation could cost lives." Walter nodded acceptance of this responsibility. He returned to Station 47 the next morning and began installing every tail assembly bolt 3 degrees off specification, creating unauthorized improvements to aircraft that would soon face the Luftwaffe's finest pilots over the most heavily defended targets in Nazi Germany. Boeing's structural testing laboratory occupied a vast hangar in Plant 1, where engineering teams subjected aircraft components to stresses that simulated combat damage, aerodynamic extremes, and catastrophic failure scenarios. Wing sections were bent until they snapped. Fuselage panels were shot with machine gun fire to test penetration resistance. Tail assemblies were twisted, compressed, and subjected to loads that exceeded any force they would encounter in operational service. This was where theory met material reality, where mathematics either held or surrendered to physics. On September 22, 1942, 8 days after Walter's initial discovery, Morrison presented the misaligned joint to senior engineer Thomas Keller, a Caltech graduate who approached aircraft design with the absolute confidence of advanced education and rigorous calculation. Keller examined Walter's work with visible skepticism. Factory workers did not improve upon Boeing's engineering staff, particularly not through deviation from specification. "You're telling me an incorrect installation is superior to our design?" Keller's tone carried the institutional dismissal of unauthorized innovation. Morrison, who remembered his own years on the production floor, responded carefully. "I'm telling you the empirical testing shows unexpected strength. I'm requesting formal analysis before we dismiss it." They mounted both assemblies, standard and deviated, in the structural testing frame. Hydraulic rams applied precisely calibrated loads while strain gauges measured deflection, stress distribution, and failure points. The testing protocol was exhaustive. Vertical loads simulating aerodynamic forces during steep turns, lateral loads simulating rudder deflection, torsional loads simulating the violent maneuvers bombers executed to evade fighter attacks. The standard assembly performed exactly as designed. Strong, reliable, meeting every specification. It would carry a B-17 through combat and return the crew safely, assuming battle damage remained within survivable parameters. The misaligned assembly performed better, not marginally, 14% reduction in maximum deflection, 9% improvement in load distribution, and a failure point that exceeded the standard design by 320 foot-pounds of torque. The 3-degree deviation engaged a secondary load path through the lower fuselage structure that the original design had left underutilized. Walter's hands had discovered what Boeing's engineers had missed. Keller stared at the data with the expression of a man watching his calculations betray him. Morrison waited, allowing the numbers to speak. Finally, Keller looked up from the test results. "This changes everything," he said quietly. "If this holds across full aircraft testing, we've been delivering inferior bombers for 8 months. How many aircraft have gone operational with the standard assembly?" Morrison checked production records. 417. The decision ascended Boeing's hierarchy with the urgency of discovery that war accelerates. By September 25th, the test data reached Philip Johnson, Boeing's chief aeronautical engineer, and William Allen, the company's president. They faced a calculus that balanced engineering pride against operational necessity, admit their design was suboptimal, and implement an improvement discovered by a factory worker, or maintain the existing specification and accept that American bombers were flying with tail assemblies that could be stronger. Allen, a lawyer who understood institutional liability, asked the question that mattered. If we don't implement this change and a B-17 loses its tail section in combat, can we be held responsible for not using the better design? Johnson, who carried responsibility for 17,000 lives flying in aircraft bearing his engineering stamp, answered with engineer's precision, "If the improvement is real and we suppress it, we're complicit in every preventable loss." The decision took 4 minutes. Implement immediately. Retrofit all operational aircraft during scheduled maintenance. Issue technical directive to all B-17 production facilities. Boeing's plants in Seattle and Wichita, Douglas Aircraft in Long Beach, Lockheed Vega in Burbank. The modification would become standard across all Flying Fortress production effective October 1, 1942, but recognition required documentation, and documentation required credit. Johnson insisted that Walter Kowalski be named on the engineering change order, unprecedented for a factory worker, standard practice for engineers. Allen agreed, then went further. Walter would receive a war bond, a formal commendation, and permanent assignment to Boeing's quality improvement team, where his practical knowledge could identify other optimization opportunities. On September 28th, Philip Johnson visited Station 47 personally, accompanied by Frank Morrison and a photographer from Boeing's public relations department. The production line continued its relentless rhythm, another bomber every 8 hours, while Johnson shook Walter's hand in front of 40 workers who had paused to witness management acknowledging shop floor expertise. "Mr. Kowalski," Johnson said clearly enough for the assembled workers to hear, "you have improved the B-17 in a way our engineering team missed. Your modification will be implemented across the entire fleet. The Army Air Forces estimates this will save hundreds of lives over the course of the war." Walter, uncomfortable with attention, replied with characteristic humility, "I just installed it the way it felt stronger, sir. The bomber did the rest." But everyone present understood what had occurred. The democratization of innovation, the recognition that expertise resided in hands as well as minds, and the acknowledgement that winning required listening to those who built the machines as carefully as to those who designed them. The technical directive, Engineering Change Order 47K, reached operational B-17 squadrons in England on October 15, 1942, accompanied by detailed retrofit instructions and priority classification that placed it above all maintenance activities except critical repairs. The 8th Air Force, commanded by General Ira Eaker, was still building operational strength, flying increasingly dangerous daylight raids against Nazi-occupied Europe, while the Luftwaffe defended with skilled pilots and overwhelming numerical advantage. At Grafton Underwood Air Base, 90 miles north of London, Technical Sergeant Robert Chen oversaw maintenance for the 97th Bombardment Group. He read EQ 47K with the weary skepticism of a man who had processed dozens of engineering changes, most addressing minor issues that made negligible operational difference. But the language in this directive was different. Critical structural improvement. Increases tail assembly survivability under combat stress. Implement immediately on all operational aircraft. Chen assembled his maintenance crews and explained the modification. Boeing saying this makes the tail stronger. 3-degree angle change on 6 bolts. Doesn't sound like much, but the testing data shows real improvement. We've got 12 birds that need retrofit before next mission. The work required 4 hours per aircraft, removing the original bolts, inspecting for stress damage, reinstalling with the specified deviation. Chen's teams worked through the night of October 15th, fueled by coffee and the knowledge that these bombers would face German fighters in 48 hours. By dawn, all 12 aircraft in the 97th's operational fleet carried Walter Kowalski's improvement. 2 days later, October 17th, those bombers flew to Romilly-sur-Seine in occupied France, targeting Luftwaffe repair facilities. The mission encountered heavy fighter opposition. Messerschmitt Bf-109s and Focke-Wulf FW-190s, attacking in waves, focusing fire on engines and tail sections to destroy control surfaces and kill pilots. The B-17s fought through, dropping their ordnance and turning for England while German fighters pressed pursuit. Aircraft 1124523, Memphis Belle, still months from fame but already collecting damage, took 20mm cannon fire that severed hydraulic lines and damaged the vertical stabilizer. The tail structure flexed violently, stressed beyond original design parameters. In a bomber with standard assembly, the structural failure would have been catastrophic. With Walter's modification, the tail held. The Memphis Belle returned to Grafton Underwood with 87 holes in a tail section that should have failed but didn't. Technical Sergeant Chen inspected the damage personally, saw where the improved joint had distributed stress away from the primary impact point, and understood that someone in Seattle had saved 10 lives without ever leaving the factory floor. News of the modification's success traveled through military channels with the velocity of information that validates innovation. By November 1942, combat reports from multiple bomb groups confirmed that B-17s with EKO 47K survived tail damage that would have destroyed aircraft with standard assemblies. The data accumulated. 14 bombers returned with catastrophic tail damage. 140 crew members survived encounters that statistics suggested should have been fatal. At the Pentagon, Lieutenant Colonel Curtis LeMay, future architect of strategic bombing, current operations analyst, compiled the survival data and wrote an assessment that would shape Air Force procurement policy for decades. The Kowalski modification represents the type of practical improvement that cannot be achieved through design theory alone. Recommend immediate implementation across all bomber programs and formal recognition that operational feedback and factory floor expertise constitute essential components of aircraft development. LeMay's memo reached General Henry Hap Arnold, commanding general of the Army Air Forces, who understood that winning the air war required not just producing aircraft but continuously improving them. Arnold issued a directive establishing operational improvement teams at every aircraft manufacturer, groups that would include factory workers, combat veterans, and engineers tasked with identifying practical modifications that enhanced survivability and effectiveness. Walter Kowalski, meanwhile, had been reassigned to Boeing's quality improvement team as promised. His new role involved walking the production lines, observing assembly processes, and identifying opportunities for optimization. In his first 6 months, he proposed 14 modifications, 8 of which were implemented. Most involved subtle changes invisible to casual inspection, but significant in their cumulative effect. A wiring route that reduced electromagnetic interference, a fuel line placement that decreased vulnerability to flak damage, a gun mount adjustment that improved traverse speed by 3 degrees. None achieved the dramatic impact of the tail assembly modification, but collectively they represented a philosophy that aircraft improvement was continuous, that expertise existed at every level of production, and that war-winning innovation came from listening to those who built and maintained the machines as carefully as to those who designed and flew them. In December 1942, Boeing's Public Relations Department published an article in Boeing News, the company newsletter, featuring Walter and the tail assembly modification. The article included a photograph, Walter at Station 47, holding the bolt that had started everything, surrounded by the bomber fuselage that his hands helped make stronger. The caption read, "Seattle worker improves B-17 survivability through practical innovation." Walter kept the clipping in his wallet for the rest of his life. The modification's implementation across the B-17 fleet accelerated through early 1943 as production increased and operational demands intensified. Boeing's 3 production facilities, plus Douglas and Lockheed Vega, manufactured B-17s at a combined rate exceeding 100 aircraft per month. Each bomber received Walter's tail assembly modification before delivery, and retrofit teams visited operational bases across England, North Africa, and the Pacific to upgrade existing aircraft. At Polebrook Air Base in England, home of the 351st Bombardment Group, the modification became part of crew briefings. Squadron commanders explained to their pilots that the tail section was stronger than previous models, that survivability had improved measurably. For young men flying into flak-filled skies above Hamburg and Berlin, this information carried weight beyond technical specification. It represented the possibility of survival, the knowledge that someone in Seattle cared enough to make their bomber better. Lieutenant William Thompson, pilot of B-17F DER 42-300234, named Devil's Advocate, flew his first combat mission on February 27, 1943, targeting the U-boat pens at Wilhelmshaven. The mission encountered heavy flak and sustained fighter attacks. Devil's Advocate took a 20mm shell through the vertical stabilizer that severed control cables and damaged the rudder. Thompson felt the aircraft yaw violently, fought the controls, and discovered he could maintain directional control despite the damage. The tail hadn't failed. The structure held. He limped back to Polebrook with half his rudder gone and a tail section that looked like it had been chewed by some massive predator. The ground crew swarmed the damaged bomber, assessing whether it could be repaired or should be salvaged for parts. Master Sergeant Paul Wilson, crew chief for Devil's Advocate, examined the tail structure and found the critical difference. The modified joint had distributed the impact stress away from the control cable attachment points. A standard assembly would have failed completely, sending the aircraft into an unrecoverable spin. Wilson documented the damage photographically, standard procedure for combat analysis, and filed his report with technical intelligence officers who compiled data on aircraft survivability. His conclusion was unambiguous. Aircraft survived due to improved tail assembly structure. Recommend commendation for modification designer. That report joined dozens of similar assessments flowing from operational squadrons to Air Force headquarters to Boeing's engineering offices. Each documented instance where Walter's modification had prevented catastrophic failure, where a 3-degree deviation from specification had preserved 10 lives and a $1 million bomber. The data accumulated. The evidence became overwhelming. Walter Kowalski's hands had changed the war. By summer 1943, the tail assembly modification had become so thoroughly integrated into B-17 production and operations that most crews never knew the design had been different. For them, the Flying Fortress simply was what it was, a bomber that could absorb punishment and keep flying, that brought them home from missions that destroyed lesser aircraft. The modification had become invisible through complete adoption, but in Boeing's engineering offices, Walter's discovery had catalyzed a broader transformation in how the company approached design improvement. Philip Johnson established a formal program called Production Innovation Review, where factory workers could submit proposed modifications with guaranteed engineering evaluation. The program generated 63 implemented changes in its first year, addressing everything from manufacturing efficiency to combat survivability. The cultural shift was significant. Boeing had always valued precision and adherence to specification, essential qualities in aircraft production where deviations could prove fatal. But Walter's experience demonstrated that specifications, no matter how carefully calculated, represented starting points rather than end points. Improvement required dialogue between those who designed and those who built, recognition that theoretical optimization and practical optimization sometimes diverged. Other manufacturers adopted similar programs. Douglas Aircraft created builders' advisory boards, where assembly workers met monthly with engineers to discuss potential improvements. Consolidated Aircraft, producing B-24 Liberators, implemented a field feedback loop that channeled combat reports directly to both engineers and production supervisors, ensuring that operational experience informed manufacturing decisions. The cumulative effect across American aircraft production was substantial. A study conducted by the Army Air Force's Materiel Command in August 1943 found that factory-originated improvements had increased bomber survivability by an average of 11% compared to original specifications. These modifications, most invisible to casual observation, all significant in aggregate, represented the practical genius of American manufacturing, the ability to iterate, to improve, to recognize that expertise resided at every level of the production system. Walter Kowalski continued his work at Boeing, eventually training other workers in structural observation and quality assessment. He never sought publicity beyond that one newsletter article, never claimed heroism for installing a bolt incorrectly. When colleagues asked about the modification, he deflected with characteristic humility, just did what felt right. The bomber proved it worked. But Boeing's leadership understood what had occurred. In December 1943, William Allen presented Walter with a personal commendation and a war bond worth $1,000, substantial money in 1943, though inadequate compensation for saving hundreds of lives. The ceremony was brief, conducted on the production floor with minimal disruption to the relentless rhythm of bomber assembly. The true measure of Walter's modification emerged not in any single dramatic rescue, but in the accumulated statistics of survival compiled throughout 1943 and 1944. The 8th Air Force conducted detailed analysis of bomber loss rates, categorizing failures by type: enemy fighters, flak, mechanical failure, weather, and unknown causes. Within each category, analysts examined specific failure modes: engine loss, fuel system damage, structural collapse. Tail section failures showed remarkable decline after ECO 47K implementation. In 1942, before the modification, 7.3% of B-17 losses resulted from tail structure failure following combat damage. By late 1943, after fleet-wide implementation, this percentage had dropped to 2.1%. The improvement was statistically significant, operationally meaningful, and directly attributable to a 3-degree deviation from original specification. Major Gerald Hansen, Chief of Bomber Survivability Analysis for the 8th Air Force, wrote a classified report in March 1944 that quantified the impact. Implementation of tail assembly modification ECO 47K has prevented an estimated 237 catastrophic structural failures, preserving 2,370 aircrew lives and 237 B-17 aircraft valued at $475,000 each. Total operational value of modification: $112 million plus immeasurable morale benefit of increased crew confidence. Hansen's report recommended that Walter Kowalski receive the Medal for Merit, the highest civilian decoration for wartime service. The recommendation ascended through military bureaucracy, but ultimately stalled at the War Department, where officials concluded that recognizing a factory worker's contribution at such elevated level might create precedent issues. Instead, Walter received a citation from the Army Air Forces thanking him for his significant contribution to bomber survivability and operational effectiveness. He framed the citation and hung it in his garage next to his union card and his citizenship papers, 3 documents that represented his American experience: labor, belonging, contribution. Meanwhile, B-17s continued flying missions over Europe with Walter's modification incorporated so completely that most crews never knew his name. They knew only that their fortress could absorb damage that would destroy other aircraft, that the tail held when it should have failed, that they made it home when statistics suggested they shouldn't. In April 1944, Memphis Belle completed her 25th mission and returned to the United States for a publicity tour, becoming the first B-17 to finish a full combat tour. Among her many documented instances of battle damage was that October 1942 tail strike that should have been catastrophic. Walter Kowalski never knew that his modification had helped make Memphis Belle famous. He was too busy improving other aspects of B-17 production. The modification's ultimate validation came not in peacetime analysis, but in the desperate skies over Germany during the most brutal phase of the strategic bombing campaign. The 8th Air Force's missions to Schweinfurt, Regensburg, and Berlin in late 1943 and early 1944 encountered defensive firepower that exceeded anything previously experienced. Hundreds of flak guns, swarms of German fighters piloted by veterans who had learned to exploit every weakness in American bomber formations. On March 6, 1944, during the first major raid on Berlin, B-17G, Ursache 42, 97061, named Flak Magnet, took direct hits from 3 80mm shells during the bomb run. One shell detonated beneath the tail section, sending shrapnel through the vertical stabilizer and horizontal stabilizers. The entire tail structure flexed violently, twisted beyond designed stress parameters, and should have separated from the fuselage. It held. Lieutenant Robert Shaw, Flak Magnet's pilot, felt the impact, heard his tail gunner scream over the intercom, and prepared for the aircraft to enter the death spiral that tail section loss always produced. Instead, the bomber remained controllable. Shaw could feel the damaged structure through the control column, sluggish response, heavy pressure required for corrections, but the tail remained attached. He turned for England with 270 miles of hostile territory ahead and a tail section that defied physics by not killing him. The flight back took 3 hours of constant control inputs, fighting a damaged aircraft that wanted to roll and yaw, burning fuel at an alarming rate because he couldn't maintain optimal altitude. Shaw landed at the emergency field at Manston with his fuel gauges reading empty and his hands cramping from control pressure. When he finally shut down engines and climbed from the cockpit, he looked at his tail section and couldn't comprehend how it remained attached. The subsequent damage assessment documented the survival, The modified joint had distributed the explosive force across secondary structures that the original design left underutilized. Standard assembly would have failed at the primary attachment points. Walter's 3-degree deviation had created a load path that absorbed what should have been catastrophic damage. Shaw's entire crew, 10 young men who should have died over Berlin, walked away from Flak Magnet that day. They went to debriefing, filed their combat reports, and returned to quarters where they tried to process the fact that they had survived something unsurvivable. Most never learned about EKO 47K or Walter Kowalski. They simply understood that B-17s were tougher than anyone believed possible. As the war in Europe approached its conclusion in early 1945, the accumulated evidence of Walter's modification became irrefutable. The Army Air Force's Statistical Control Division compiled comprehensive data on B-17 combat effectiveness, and the numbers told a story of gradual but significant improvement in survivability. Aircraft manufactured before October 1942 showed baseline loss rates. Aircraft with EKO 47K showed measurably better survival, particularly in scenarios involving tail damage. The improvement wasn't merely statistical, it was personal. Every crew that limped home in a damaged bomber, every gunner who survived a direct hit to his position, every pilot who managed to control an aircraft that should have been uncontrollable, represented the tangible outcome of one factory worker's decision to trust his hands over blueprints. In April 1945, as Allied forces crossed the Rhine and Soviet armies closed on Berlin, Boeing began transitioning from wartime to peacetime production. The lessons learned during 4 years of combat-driven innovation would shape commercial aviation for decades. The culture of continuous improvement, the recognition that expertise existed at all levels of production, the understanding that specifications were living documents rather than sacred texts. These principles became embedded in Boeing's institutional approach. Walter Kowalski, 51 years old by war's end, continued working at Boeing through the transition. He participated in the development of the B-50 and later the B-52, always bringing his practical perspective to engineering discussions. His contributions became routine rather than revolutionary, but their cumulative impact remained significant. Designers learned to consult production workers during initial phases, to test assemblies for both theoretical and practical optimization, to recognize that the best aircraft emerged from collaboration rather than hierarchy. In 1952, Boeing published an internal history of its wartime production improvements. The chapter on EKO 47K included interviews with Walter, combat pilots who had benefited from the modification, and engineers who had validated its effectiveness. The conclusion was understated but clear. Mr. Kowalski's observation and subsequent modification prevented hundreds of catastrophic failures and demonstrated the value of integrating production expertise into design processes. Walter retired from Boeing in 1967 after 25 years of service. His personnel file contained 43 implemented modifications, dozens of commendations, and one newsletter article from 1942. He never spoke publicly about his contributions, never sought recognition beyond what Boeing provided, never claimed to have changed the war. When his grandson asked about his Boeing career, Walter's response was characteristically modest. "I built bombers, did it the best way I knew how." The full significance of Walter Kowalski's modification crystallized decades after the war, when aerospace historians began analyzing the factors that enabled American strategic bombing to succeed despite horrific loss rates. The B-17 Flying Fortress had entered service with genuine vulnerabilities. Early models lacked adequate armor, defensive armament, and structural resilience against the punishment that German flak and fighters inflicted. Yet by war's end, the B-17 had become legendary for survivability, for bringing crews home despite damage that should have been fatal. That transformation resulted from hundreds of incremental improvements, most documented only in technical directives and engineering change orders. But EKO 47K stood out for its simplicity, its impact, and its origin. A 3-degree deviation from specification, noticed by hands that knew metal and stress, implemented across thousands of aircraft, and validated by hundreds of crews who survived tail damage that the original design couldn't withstand. In 1995, the Smithsonian National Air and Space Museum curated an exhibition on wartime aircraft innovation. Among the artifacts was a tail section from B-17G 42-97061, Flak Magnet, showing the battle damage Robert Shaw's crew survived over Berlin. The exhibit placard explained the structural modification and credited Walter Kowalski by name, noting that his practical observation had improved the B-17's survivability during the most critical phase of the air war. Walter attended the exhibition opening at age 91, accompanied by his daughter and grandson. He stood before the damaged tail section, the physical evidence of his contribution, and studied the twisted metal and repaired structures. A museum visitor reading the placard asked if he was the Kowalski mentioned in the text. "Yes," Walter replied quietly. "I installed those bolts." The visitor, a former B-17 pilot who had flown missions in 1944, looked at Walter with sudden recognition. "You made the tail stronger. I heard about that during combat training. They told us the B-17 could take a beating because someone in Seattle had figured out how to build it better." Walter nodded, uncomfortable with the attention. "Just felt stronger that way. Seemed right to use it." The pilot extended his hand. "I flew 35 missions and came home. Maybe your modification had nothing to do with my survival. Maybe it did. Either way, thank you." They shook hands, two old men connected by aluminum and war and the simple arithmetic of survival, standing in a museum that preserved what Walter's hands had helped create. Walter Kowalski died in 2001 at age 97, having lived long enough to witness the Cold War, the space race, and the transformation of aviation into the jet age he had helped build. His obituary in the Seattle Times mentioned his wartime work at Boeing and his contribution to B-17 survivability, though most readers likely skipped past it. Another elderly veteran, another member of the generation that won the war, passing into history. But in aerospace engineering circles, ECO 47K remained a case study in practical innovation, taught at MIT and Caltech, and in Boeing's own engineering training programs. The modification represented a principle that transcended its specific application. That optimal design emerged from dialogue between theory and practice, that expertise resided in unexpected places, and that the best solutions often came from those closest to the physical reality of construction. The B-17s that Walter helped improve flew their last combat missions in the 1950s, replaced by jet bombers with capabilities that would have seemed impossible in 1942. But the cultural transformation his discovery catalyzed, the recognition that production workers' knowledge constituted essential design input, continued shaping American aerospace development. When Boeing engineers designed the 747 in the 1960s, they institutionalized production worker consultation. When NASA developed the space shuttle, factory floor expertise informed engineering decisions. The principle had become doctrine. Lieutenant Robert Shaw, who survived Berlin and flak magnet, never forgot the sound of 80 mm shells detonating beneath his tail section, or the impossibility of that structure remaining attached. He spent 30 years as a commercial pilot, flying Boeing 707s and 727s, always aware that he owed his career to aluminum joints modified by a factory worker he never met. In 1989, he wrote to Boeing requesting Walter's address. They corresponded briefly, Shaw thanking him, Walter deflecting credit. Before Shaw's death in 1993, the tail section from Flak Magnet remains in the Smithsonian collection, occasionally displayed in exhibitions about wartime innovation. The placard still credits Walter Kowalski, still explains the 3-degree deviation, still notes that this simple modification saved hundreds of lives. Sometimes the most significant innovations are invisible, 3 degrees of deviation, imperceptible to the eye, profound in consequence. Sometimes expertise speaks through hands rather than equations, and sometimes winning requires listening to those who build as carefully as to those who design. Walter Kowalski installed a bolt incorrectly and made history stronger. His hands knew what blueprints had missed, that survival often depends on the small adjustments we make when something doesn't feel quite right.